Spreadsheets have a variety of applications in education, and this project is going to require you to develop your own spreadsheet for teaching a particular concept. The concept that I'm going to talk about right here is calculation of bond energies. And so first, a little bit of the background on the chemistry of this, and then we'll actually get into the spreadsheet development. Whenever you have a chemical reaction, such as the burning of methane, a natural gas here in a Bunsen burner, there's a chemical reaction which involves the breaking of bonds as well as the forming of new bonds. And by knowing the total of the bonds that are broken and the value of each of those bonds, and the bonds that are formed and the value of each of those bonds, we can calculate and see what the net energy gain or loss is in the system. So a little the foundational chemistry. Here we have a reaction where we take methane plus oxygen and we're producing carbon dioxide and water. This is one of the most common reactions that there is out there, one of the most common oxidation reactions. You will see this on your stove. So for example, on a stovetop, the blue flame that you see is actually the methane as it's combusting to produce carbon dioxide and water. So the reaction might look something like this, where you take one methane molecule, CH4, you combine it with two oxygen molecules here, and the atoms are rearranged to produce two water molecules, H2O, and one carbon dioxide molecule, as you're seeing over here. So the question is that how much energy is released from that? And we can see normal calculation values and so forth like this you might see printed in textbooks. And students will look at this and eyes will glaze over, and they won't really get an idea for where those numbers came from or what their significance is. But the spreadsheet, we can make this, I think, a little bit more meaningful. Whenever you have a chemical reaction, bonds are broken, and it takes energy to break those bonds. And then bonds are formed, and you get energy out from those bonds as they're formed. Now, if we happen to know what the cost is in terms of breaking a carbon-hydrogen bond, and we know the quantity of those, for example, in this case, there's 4, 1, 2, 3, 4, and we know what the cost of breaking the oxygen bonds are, in this case, 2 oxygen double bonds, and then the benefit that we would get by forming new bonds, in other words, the energy that is put into the system from the formation of like 2 carbon-oxygen double bonds and 4 oxygen-hydrogen bonds. We can do a system, basically a ledger of pluses and minuses to figure out what the net value is for the reaction. And so you've probably seen methane burning not only on the stove, but maybe if you've ever driven past an oil rig or something like that, you can see excess methane being burned off. And we want to be able to see, is there actually a net gain or loss in energy to the system as a result of this oxidation? So we're going to look at some kind of a free energy diagram. Now, you don't need to understand the chemistry to understand kind of the idea of using the spreadsheets. This is simply an example to give you the idea for how this works in terms of using a spreadsheet and teaching. So behind here, we have a blank spreadsheet, and you're going to be working with a blank spreadsheet and putting the values and so forth into that spreadsheet. Now, I might happen to know something about bond energy and so forth, and so going to a table of bond energies, I could put in some values there for bond energy there for some typical bonds. And I'm going to close the ribbon here so I can see all of my table there a little bit more precisely. Now, if I know the energy of those bonds, okay, which I will just put here in the next column, or actually one more column over, I can see that a carbon-carbon bond is, to break a carbon-carbon bond, is going to cost me 347 kilojoules per mole. So the question is how many bonds are going to be initially broken or formed. So I'm going to start here on the input side, and this category here, or this column, that represents the number of bonds in the system. And so again, just to make this make a little bit more sense, we should probably give it an appropriate title. So everything you're seeing here in blue refers to bonds that are broken. Now, as in any kind of ledger, there's going to be costs, as we've shown right here, and there's going to be benefits. And we're going to put the benefits right over here in the column in red. And notice that when I do this here, that the values here in red have exactly the same numeric values as the ones in blue, because bond energies have the same strength. And so if it takes 347 kilojoules per mole to break a bond, then by that bond formation you're going to get 347 kilojoules out of the system. So again, in the concept we have right now is that we're starting with 0 bonds broken, 0 bonds formed. So let's go back and talk about the actual reaction we're talking about here, which is the combustion of methane. So methane is oxidized, so the CH4 molecule here is combusted or oxidized to produce carbon dioxide and 2 water molecules, as you can see from this reaction here. That's going to take place on any Bunsen burner, or going to take place in any time where the methane is combusted in the presence of, well, combusted with oxygen. So we're going to just write the reaction over here as a sample reaction so we can see what it is that we're really talking about. So over here I'm going to paste in the formula for actually this balanced reaction of 1 methane plus 2 oxygens is going to 1 carbon dioxide plus 2 water molecules. Now, to actually do the calculations, we need to put in some other values and so forth into the system. So first of all, we're going to talk about the total energy in the system. Okay, in other words, total energy, and we're going to say, okay, how many kilojoules do we have in this the system that are going to be required to break the bonds? How many kilojoules are we going to get out from the system? So when we're looking at this, that the values here at the bottom are going to represent the energy in and the energy out from the system. So first of all, in terms of breaking the bond energy, how would we put those values into the system? Well, we probably need another column, okay, and we have another column right here. We're going to call this the total energy to the system. So the total energy which is going to be required from the system. We can change the widths of these by going up to the little dividers between the category headers here and simply stretching them. And I'm going to insert another column here, insert another column just so we can have a little bit more space in there between the bonds that are broken and the bonds that are formed. Okay, so now as we're building this spreadsheet, we need to start to figure out, okay, what kind of values should we have? So we're looking at this and we're saying, okay, well, what we really need to figure out is the total energy here for the bonds that are going to be broken is going to be equal to, and I'm going to type in an equal sign, the energy per carbon-carbon bond, in this case 347, so I'm simply going to click on that cell, and that's going to insert C7, meaning whatever the value of C7 is, take that. Then multiplied, which is simply an asterisk, times the number of those bonds. And so I'm going to put in a click on this cell here. And so my formula, which shows up in D7 as well as up here in the formula bar, shows that I'm taking the energy per bond and multiplying it times the number of bonds in the system. So when I press enter, we can see that the total value there obviously is 0. But if I was to change that and say, okay, how about if there was 1 bond you can see it'll return the value 347 or 2, and it's going to return 694. So you can see that the math is actually going correctly. Now, I want to format this in the same form that I've formatted the others. So to do so, rather than trying to figure out what font size and so forth, I can use the formatting brush right here, where it says copy the formatting from one cell to another. So I'm going to click on this, and I can simply drag over here, and you'll see that D7 now assumes the same formatting as the source, C7. Now, I could go about the laborious process of re-entering that value all the way down, but I realize that if I could copy this in a relative fashion, I could do things a lot simpler, and that's what I'm going to do here. I'm going to take the value here of C7 times B7, and I want to copy this down. So to do so, I'm going to move my cursor over the lower right-hand corner of the cell, and I'll simply drag this down. In the process, I've copied the formula down, and so what was initially C7 times B7 should be now here C8 by B8 in cell D8, or it'll be C9 times B9 in cell D9. And so we've done a relative copy. Again, we can repeat that process over here. We can simply say, okay, equals the number of bonds, H7, times, and then the number of bonds, simply click on that cell, G7, and hit enter. And again, we return 0. By clicking on this cell and by taking the formatting paintbrush, I can drag this across, and I now have the same formatting cell parameters, and I can copy this down, and I can see that once again I have my same format with the values there. And I will simply title this also total, and we now have the basics for our calculations. So well, this is nice, but we haven't really calculated total energy in and total energy out from the system. So we can do that by simply finding out what the values are for this column here. In other words, column D is going to give me the total for all the individual bonds that are broken, and collectively we can get them for the whole column. So I'm going to say equals the sum of whatever the values are. The beginning of the parentheses tells me to take the beginning value. I'm going to click on the first entry and simply drag down. Now you can see the entry there says D7 to D6, and there's that entire range, the colon indicating the range. If I put the end parentheses and hit enter, then we can see that the total value is going to be here in the bottom, and we're going to label this here. I think I'll put this over here in a light blue to be more consistent with the colors, at least that I've chosen right here, and I'll choose this over here to be in a light red so we can see the values over there again consistently with what appears up above. So let's say that we're talking methane. Okay, methane is CH4. That means that there's 4 carbon-hydrogen bonds that have to be broken because there's no carbon-hydrogen bonds on the other side. So I'm going to put 4 carbon hydrogens right here, and that's going to cost me, oops, obviously the value is coming up there 4, that's an error. I can just say there's 4 bonds over here, that's the number, so I'm going to type in there 4 bonds right there, which now is going to cost me 1,652 kilojoules per mole, and that's going to appear down at the bottom. Now, in addition, I have to break 2 oxygen-oxygen double bonds. Again, if we look back at the formula right here, that we had 2 oxygen-oxygen double bonds which appear on the left but nowhere appear on the right. We have a carbon-oxygen double bond. In fact, we have 2 of them, but we have no oxygen-oxygen double bonds. So what we have to do in this case right here is we have to subtract out of this, in other words, a negative here of 2 oxygen carbon bonds. So by putting here the number 2 and hitting enter, okay, we can see now that cost is 1,610 for a total cost of 3,262 kilojoules for the input. So that's what's going to take to break the bonds. In other words, over here, if we're breaking the 4 carbon-hydrogen bonds and the 2 oxygen double bonds, the total cost of that is 3262. So there's a lot of energy which is input into the system. So, well, what do we get out of the system? Is there any output from the system? Well, to determine that, let's go ahead and do the same thing on the other side, because we're getting 2 carbon-oxygen bonds. Again, to illustrate that, you get 2 carbon-oxygen double bonds plus 1, 2, 3, 4 oxygen-hydrogen single bonds. So if we put over here the number of carbon-oxygen double bonds, go over to carbon-oxygen double bonds, a total of 2, that's going to give us out 704. Well, we're still not up to where we need to be. Oops, that was the wrong thing. That was carbon oxygen over here. I should have put on the reverse side. We didn't break carbon-oxygen bonds. Instead, on this side, we broke oxygen-oxygen bonds. And so that's the cool thing about spreadsheets, is we can go back and we can make our corrections right there. And by changing that now, I just caught my own error, and I have a new value down there. In other words, we broke oxygen-oxygen bonds. That's what we're seeing right here. And we broke 4 carbon-hydrogen bonds, and you broke that right there. So you see here how I just caught my own error by using the spreadsheet. So it's very simply able to adjust it by putting the number in the correct cell. And spreadsheets, of course, when they're configured correctly, allow you to do that very simply. Now again, we have 4 hydrogen-oxygen bonds being produced from this, so I need to find the hydrogen-oxygen bonds and put a value of 4 here. And we can see now that we have what our total output is going to be on the other side. So to determine the value of energy which is released from the bonds formed, we would simply do an equals in this column right here in I-27, and the sum of the range between the first possible entry, the carbon-carbon one, all the way down to the last, the oxygen-oxygen double bond. Again, hitting the in parentheses and the enter. And I will also just copy over the formatting one more time here so you can see how that works. So right now, we can look at this and we can say that to combust a mole of methane is going to cost us 2,620 kilojoules. And the result is I'm going to produce 3,466 kilojoules. So even though it costs me something to burn it, I'm getting more out of it than I'm putting into it. Now we could do a final calculation over here where we just simply say total energy in, and then versus total energy out, and finally versus the energy change. So adjusting the column widths over here, and making these things again consistent. So I'll grab the formatting from this. This is my energy in. My energy out I'll grab from right here. Grab the paintbrush. Here's my energy out. And I'm going to change this one right here to a different font color here. I'll choose this black with a yellow background here. And so now we can look at this and say, okay, what would the total value be? So this one right here would simply say equals whatever the value is that we got right here. So simply click on that, hit enter. Then take equals here for the total energy out, go find that right here. So we're simply referring that number over. And now what we do is we say, okay, equals the total energy in minus the total energy out. So it's L3 minus L4, hit enter. And so we can see here we have a negative 846 kilojoules coming out. The idea is we could also give some kind of explanation for this. Positive energy change shows an endothermic reaction, negative number shows an endothermic reaction. And now we have a table that can work for many different purposes. We're basically looking at energy changes in chemical reactions, and as we choose our chemical reaction, we can put in whatever values we want to, and just the simple numbers of the bonds that are broken and the number of bonds that are formed. We can do a balance sheet, and we can see if it's going to be an endothermic or exothermic reaction. Now, this is basic to understanding thermodynamics and chemistry. I realize this is a very specific application to chemistry, but it shows you how spreadsheets work, how the formulas are placed in, and how you can reference the values calculated in other cells to come up with a net values as desired. So this is just one of many, many, many different options for how to use a spreadsheet to teach some concept in a particular discipline. And so what you want to do is be able to develop a spreadsheet to teach a concept relevant to your own teaching as much as possible.